Hi everyone. Today we'll take a look at geometric series. So, the geometric series is the sum of n terms of a geometric sequence. Now, let's look at it in a bit of detail. So, now if we had, for example, a sequence, right? Suppose we had u1, u2, u3, all the way up to un, right? So now if we take the sum of this entire sequence, right, that gives us a geometric series, and we could denote it as S of n is equal to u1 plus u2 plus u3 all the way up to un. Now, if I had to write this in terms of a geometric sequence, what I can do is I can write each term in the sequence as u in the form of u1 times r in raised to the power n minus 1. So if I do that, what we get is u1 plus u1r plus u1r squared all the way up to un. Sorry, I meant just write u1 r raised to the power n minus 1, right? This is our essentially what you could call as a general sequence to give you a basic idea of what a geometric series is about. It's very similar to what you would call an arithmetic series, right? In that case, you had u1, u2, u3, but instead of u1r, u1r squared, you would have u1 plus d into n minus 1, right? That is the only difference. Otherwise, everything remains quite the same. Right now, let's before I talk about the formulas from the data booklet. Right, there are two formulas. If you have taken a look at it, now I would like to bifurcate those two formulas first. Right, so in a geometric sequence, we can differentiate any sequence depending on the common ratio it has. Right, so if the common ratio is greater than 1, and if it's between 0, like this. Okay, so this is often called a divergent series. Okay, divergent. And this, when the common ratio is between 0 and 1, is called a convergent series. Okay, and I'll explain that as well. So when we have a divergent series, when our common ratio is greater than 1, suppose let's take 1.5, 2, or 3, or even 10 for that matter, right? Every time we multiply that common ratio with the previous term, that number will increase, right? So if we have, 1 as our first term, and then we multiply it by 2 because that's our common ratio, we'll get 2, 4, 8, 16, 32, 64, and so on and so forth. But instead of having the common ratio as 2, what if we had our common ratio as half, right? So if our first term was 1, our second term would be 1/2, 1/4, 1/8, 1/16, 1 by 32. And you could, notice that the terms will get smaller and smaller as we move forward, right? They go really, really small. And what happens in a convergent series, as the number of terms increase, you can notice that the value of the terms gets so small that they're almost negligible, right? And because they're negligible, we can ignore them. Right now, I'll get more into detail when we talk about the formula itself. So first, I'll be talking about sum of divergent series. So sum of divergent series is a quite straightforward pattern. You'll have a formula. You should know what each term represents, and you should know what things to plug in, what factors, what things you want to plug in, and what variables you want to ignore. It's as straightforward as. So let's get started with divergent series first. So we have sum of divergent series. Now, I'll just make a note here that the modulus of the common ratio must be greater than 1. Previously, I talked about just the common ratio should be greater than 1, but this is actually the true case, right? I just wanted to keep it simple at this point, so that's why I didn't mention it, but this is what the true meaning is, right? So when I say the modulus of the common ratio should be greater than 1, right? Mod r should be greater than 1. What I mean is that r should be greater than 1, or r should be less than -1, right? If you think about it logically, you can pause the video right now. Okay, you can think about this very logically. If this is only satisfied when modulus of some or common ratio should be greater than 1. So you can take 2, 3, 4, 5, 6, and or any decimal or fraction for that matter between which is greater than 1. You can take 1.5, 1.7, you know, anything, right? And the value should also be less than minus 1. So it should be minus 1.5, minus 2, minus 10, minus 100, right? As long as you satisfy this condition, it is okay, right? That is the key part. If the common ratio is greater than 1, or if the common ratio is less than minus 1, then we have what is called a divergent series, okay? We have what is called a divergent series. All right. So if we have a divergent series where our common ratio, or sorry, the modulus of the common ratio is greater than 1. So what we can write it as, and this is found in the data booklet as well. So it's the sum of n terms is equal to the first term times 1 minus the common ratio raised to the power n upon 1 minus r. Now, this can also be written as S of n is equal to u1 r raised to the power n minus 1 upon r minus 1, right? It's the same thing, right? I'm just going to put like a double arrow here. It's the same thing. Doesn't matter because all I've done is I've just multiplied minus 1 on the numerator and denominator. So these two terms interchange their positions. Either way, you can remember any of them. It doesn't matter. Okay, so now let's write everything, all the corresponding things that are important to this part. Okay, so we have S of n, which is sum of n terms, right? That's the first part. Then we have our u1, which is first term. Then we have r, which is common ratio. And we have n, which is the number of terms. Now, if you notice, previously when I was talking about arithmetic series, I did a small derivation talking about how we get to the formula for arithmetic series. But here I did not. I just directly gave you the formula because uh, the derivation is a little different, right? It's not as easy to follow, so I skipped that part. Okay, cool. Now, so again, it's a very formula-based thing. There's nothing, too fancy about it. It's very similar to, the applications will be quite similar to uh, the arithmetic series portion. Like I said in the previous video, you can treat this as an analogy if you would like. And yeah, that's about it. So now let's go to the next part, which is sum of divergent series. Sorry, I meant convergent. So here, like I said previously before, we had zero common ratios between 0 and 1, right? But here what I'm going to do is I'm going to write modulus of the common ratio is less than 1, right? So when I say modulus of r is less than 1, what I actually mean is the common ratio is between minus 1 to 1, right? This is what it means. And this is, again, like I said before, it gets a little tricky, right? Why? Because when you're multiplying by values such as 1 half, 1 by 4, 1 by 6, what happens here is you encounter what is called an exponential decay. So if I had to, show this graphically, right, what would happen is actually, it would happen like something, it would look something like this. Okay, so suppose I have some big number that's here and I multiplied by half. So next time it'll be half the value. And then again it'll be half the value. And then again it'll be half the value. And then again it'll be half the value. And it'll go so small. Like it'll be like 0.1, 0.05, half of 0.05, and then another half of that. And it's gonna go so small. Like it'll be impossible to, even if you ignored these portions right here, right? Even if you ignore the values when you're adding all the dots together, right? The values of the dots, because we're doing a summation of series, right? It would make no difference because it really doesn't change the value of the sum, All right. So now I'm going to use this formula right here, and I'm going to, sort of derive how you get to the sum of convergent series. But before that, I'll just give you the formula as it is, and I'll write on that on the next page. So it is S of n is equal to U1 upon 1 minus R. Okay. Now I'll show you the derivation, right? So for the divergent series, we had the formula as S of n is equal to u1 into 1 minus r raised to the power n upon 1 minus r, right? Now let's take a look at only this part right here. I'm gonna highlight it in line color, right? This part. So now if we take a look at this part, we have 1 minus r raised to the power n. Okay, so r is taken as a fraction value, right? Which is between minus 1 and 1. So let's take, for example, 1/4, right? Let's assume r to be 1/4, okay? And what happens is when we do sum to infinity, right? Because it's a the ratio, common ratio is, less between minus 1 and 1, right? So I'd actually like to correct myself here. Instead of writing s of n, what I'm going to do is I'm going to write s to infinity, sum to infinity. So if you take infinite number of terms, the sum is going to be whatever it is, depending on the factors, depending on the values that we put in, right? So if you take the common ratio to be 1/4, right? So we'll get 1/4. Suppose we have anything. It should be anything can be the starting value. Doesn't matter if it's 1, 10, 400, 4 billion for that matter, right? Suppose if we take 1 as our first term, right? So then we would have what? 1/4, 1/16, 1/32, 1/64, 1/64, right? Sorry, my bad. Not one here. We would have 1/64 and even a smaller value thereafter, right? We don't know, right? So what happens is you can already tell that at 1/64, the value is getting so small, right? And again, it'll get even smaller. It'll get 4 times smaller because we're multiplying by 1/4. So what happens is, and we're going to infinity, right? So when we have something like 1/4 raised to the power infinity, this value itself is so tiny. It actually tends to zero. This entire portion, let me put it in a different color here. Let me put it in pink. This entire portion tends to zero. Okay, so because it tends to zero, it's basically indicating that its value is negligible and it holds no purpose, right? So we can ignore this part, right? If we ignore this part, what are we left with? We're left with 1 minus 0, which is equal to just 1, right? Which is equal to just 1. So what I did was I took this green highlighted portion, I brought it here, I gave you an example of what's going to happen as we multiplied with that common ratio, right? It's very small to the point at which we can ignore it. Because we can ignore it, the remaining portion of the green is just equal to 1. And 1 times u1 is just u1, right? Which is what I've kept right here. And so that keeps u1 right here and 1 minus r as it is. So that is how we get to this thing right here. All right, now let's look at a few example questions. Now, before I begin, I've only taken 5 to 6 example questions. This is fairly less than what I took for arithmetic series and previous videos as well. Now, majority of the questions, like I've repeatedly mentioned, are very formula based questions, right? And I don't think I need to go step by step to explain them because the IB textbooks, the resource books, I should say, are fairly explain that fairly well. So I've ignored those straightforward formula-based questions, and I've picked a variety of different questions which can arise, and which are kind of out of the box. So you get an idea of what you can expect in an IB question. Now let's get started. The first question says, determine the sum of an infinite geometric series whose first term is 35 and fourth term is 7 by 25. Okay, so you can expect questions like this quite often. Okay, and when you do, what you need to do is you need to get the key information immediately. The first key information was it said it was an infinite geometric series. Right? When we say infinite geometric series, we're looking for sum to infinity, and it also means that the modulus of the common ratio will be less than 1. Right? This is the key information right here, which we need to know the question says infinite geometric series. Okay. Second part says first term is 35 and fourth term is 7 by 25. So let's accumulate all the information we have. So we're given that the first term is 35 and fourth term is 7 by 25. Okay, so our goal is to find sum to infinity. And like I mentioned before, the formula for sum to infinity is sum to infinity is first term upon 1 minus the common ratio, right? Okay, so we already have our first term. We just have to find our common ratio, right? So let's go ahead and do that. What we can do is we can write u4, right? u4 is u1 times r raised to the power 4 minus 1, right? Given the formula from geometric sequences, which is u1 times r raised to the power n minus 1. So that gives us u1 r cubed, right? So we can use this formula right here, and what we get is u1 is equal u1 r cubed is equal to 7 by 25. Okay, now we can simplify this a bit more. Instead of writing u1, we'll write 35 r cubed is equal to 7 by 25. Okay, now if we simplify this a bit more, what we get is, to simplify this with 5, so we get r cubed is equal to 1 by 125. What I did was I simplified this. I got 5r cubed upon 1 by 25, and I divided on 5 by both sides, and I got 1 by 25. Now, if you look closely, this is actually 5 cubed. If you don't, that's okay. You can use a calculator. But if assuming that this is a paper one question, that you should get in the habit of trying to find some patterns, because in paper one, what they'll always do is they'll give you some type of pattern where numbers will work out evenly, assuming that you do all your previous calculations correctly. So, now I know that we have done the previous calculations correctly. So this has to be some sort of a cube, or it has to work out in a very nice way to give us a very, clean answer, right? You won't be chances of getting an, answer in decimal like 2.78121 that goes on forever. It's very low, especially in a paper one question, right? It's close to zero. Like I doubt there will ever be questions, but because assuming that's a paper one question, it'll come out easily. And because I've done a lot of questions, I know this is equal to 1 by 5 cubed. So I can just say that r is equal to 1 by 5. Right? These are small things that you should pick up on as you practice, right? These are small hints that IB will give you, right? Like I mentioned before, if it's a paper one question, you can expect the numbers to come out very well, right? And suppose you're doing some question like in calculus, in integration, maybe, where you're doing integration by substitution, or you're doing integration by parts. You might not seem at first that you'll get some decent substitution, which will give you a better integral. But if it's a paper one question, things will start canceling each other out, and you will get a simplified version which you can move forward with, right? Always keep that in the back of the mind. You always keep telling yourself, look, I know it might not look great at first, but I know things will cancel out and they will get easy for me to work with, and I will be able to solve the question. Keep that mentality as you move forward. It'll really, really be easy. Okay, so let's get back to this question. Now I found the common ratio, right? That is all I required, because I already had my first term. So let's use that in the formula now. So our sum to infinity will be first term, which is 35 upon 1 minus 1 by 5. Okay, so if I simplify that a bit more, I get 35 upon 4 by 5. And I can write this, I can leave it at 35 into 5 by 4, right? Whatever 35 times 5 is, it can be, I can write it. I mean, I don't need to at this point, because you get what I'm doing, but I can leave it at this, right? And if it's a paper one question especially, then I can just leave it as a fraction, and I don't need to write a decimal number. So I'll just leave it at that. You can work the rest out on your own if you feel like you need to, but you really don't need to. You got the main idea, which was, when we have an infinite geometric series, we have to use this formula. And another way to check whether your calculation was done correctly in this question was that, if it's an infinite series, our common ratio, modulus of it will be less than 1. which it was, right? So that was a double way to check. Look, I did this so far. Now I don't know if it's right, but wait, I can check right here, right? This satisfies the condition which was given in the question. So yes, I am moving in the correct manner. I'm moving the correct direction. So I just need to continue what I'm doing, right? These are small things that you can, as you do questions, you can pick up on them, and they'll really, really help you make your life easier. All right, next question. Three numbers, a plus 3a plus 1, a plus 2, and a minus 4 are three consecutive terms of a geometric sequence. Find the two possible values of the common ratio. Now, before I begin, this isn't your typical geometric series question, and I know that. It's more towards geometric sequences, but I thought it would be appropriate to put at this point because we have much more idea and much more knowledge about working with common ratios and just the overall idea of geometric sequences and series. So it's kind of an out of the box question. I highly recommend you stop the video and try it on your own. So, assuming you've given a go at it, let's get started. So, we're given three numbers in a sequence, right? 3a plus 1, a plus 2, and a minus 4. Now, again, this question might not be so obvious at first, but as I move through it, you will develop a much better understanding. Now, this is a more of a property related question, and which I will be explaining in my next video where I'm going to be talking about properties of geometric sequences. So it's okay if you don't get this question right now. Just stick with me. Okay. So now we're given that these are three numbers, right, in a geometric sequence. Now, what is the one thing that always stays consistent with a geometric sequence? Right? The one thing that always stays consistent is that every number after in a geometric sequence is being multiplied by some constant value called the common ratio, right? So let's keep that in mind, right? So what we can say here is that the common ratio is a plus 2 upon 3a plus 1, right? Suppose if we call this un plus 1 and un plus 2, right? This is some nth term, this is the term after, and this is the term after the first terms, right? So let's take this as an example. Okay, so we have one value of our common ratio. Now, what we can do is we can do one more, right? We can write this as r is equal to a minus 4 upon a plus 2, right? Now, this also means a common ratio, right? Because what does common ratio essentially mean, right? It is the term after, right? The next term upon the previous term, right? This is the ratio of them is called the common ratio. So that's exactly what I did. I took un plus 2, put it over un plus 1. And here I took un plus 1, put it un plus 2. That is all done. Now, note that because for it to be a geometric sequence, the value of the common ratio will always be constant, right? So that means this and this are equal to each other. So let's equate them, right? So what we can do is we can write a plus 2 upon 3a plus 1 is equal to a minus 4 upon a plus 2. Okay, let's solve for a. So we have a plus 2 is equal to a minus 4 upon 3a plus 1. Okay, let's open this up. So we get a squared plus 4a plus 4. 3a squared, we get a minus 12a minus 4. Let's simplify this a bit more on the right hand side. Then I'll bring all the like terms together. So we get 3a squared minus 11a minus 4. Okay, now if I take everything on the left hand side, I'm left with 2a squared minus 15a minus 8. Okay, now I'm just going to solve this. You can solve it any way you want. You can use your calculator, your quadratic formula, your factorization, whatever. I'm just going to make factors because I can see factors being formed here. So I'm going to write 2a, right? And then I can see, 8 into 2 is 16, and then 16 minus 16 plus 1 will be minus 15. So what I'm going to do is I'm going to put minus sign here. I'm going to put 8 here. Okay, so what I'm going to get is 2a into minus 8 will be minus 16, right? And to get to minus 15, I have to add 1. So I'm going to put plus 1 here. Right, so 0 gives me basic. Okay, I don't even need to write 0 at this point. I can just write 2a plus 1 is equal to 0, and a minus 8 is equal to 0. So we get a is equal to 8, and a is equal to minus 1 half. Right? Okay, so now I've only done part of the question. Right? I've only found the values of a's. Now I have to find the terms and the common ratio. So the terms that were given, the numbers that were given to me were, I'll rewrite them in a different color. I'll write them in yellow. And I'll write them as 3a plus 1, which is given to me, 3a plus 1, a plus 2, and a minus 4. A plus 2 and a minus 4. Okay, so let's take minus 1 half in this right here. Okay, so what I'm going to get is 3 into minus 1 half plus 1 minus 1 half plus 2 and minus 1 half minus 4. So what do I get is minus 3 by 2 plus 1 is minus half. Here I'm going to get is 3 by 2. And here I'm going to get minus 9 by 2. Right? These are my three terms. Now, if I just divide this term with this term, what I'm going to notice is that my common ratio is 3. Minus 3. Right? That is it. So this is my term, and this is my common ratio. Now let's do the second part, and I'll do that in purple, light purple. Okay? So we have 3a plus 1, a plus 2, and a minus 4. Okay, let's substitute the value of a. So we get 3 times 8 is 24, plus 1, 25. Here I'm going to get 8 plus 2, which is 10, and 8 minus 4, which is 4. Again, if I divide 10 with 10 by 25, or if I do 4 by 10, what I'm going to notice is that my common ratio is 2 by 5. So I've answered both parts of the question. I have found the two possible values of the common ratio, right? That is it. So this is the second question. All right, next question. We're given that summation of 7 raised to the power 3 minus I from I is equal to 1 to 6. Now, I didn't really expand upon the summation series for geometric series, right? And that was because the principle or the concept for arithmetic series and geometric series with respect to summation remains the same, right? We're given some function here, some function, right? We're given a starting point and an ending point, right? Ending and starting, start and end, right? This is our function. We just plug in, we get a series of values, and then we add them up, right? The concept remains the same, right? The only thing you'll notice is that the terms will have some common ratio instead of some common difference. That is the only thing that is different between them, right? So I didn't really expand upon that specifically like I did in the arithmetic series video, and that was the reason why. Okay, so let's do this question now. I'll take a different color. I'll take green. Okay, so what we can do, there are two ways of starting this question, right? What we can do is we can expand out all the terms, right? From I is equal to 1, I is equal to 6, and then we can add them up, right? Simple as that. Or we can take a few terms, find the common ratio, and use the formula that we have, right? Now, when is which method appropriate, right? Suppose let's take method 1. So method 1, I'll call it simple addition, right? Which was the first thing I talked about. Right? Simple addition is okay when you have a simple function, right? And when the terms are very small, right? From I is equal to 1 to I is equal to 6, right? So when simple function is there, or when there are less terms, right? We're only talking about 6 terms here: 1, 2, 3, 4, 5, 6. That's it. Now, when is this not appropriate? Well, when there are about 100 terms, what are you going to do then? You can't sit down, write all of them out, and count them, right? That would be really tedious work, especially if this is a paper 1 question, right? And I'm pretty sure this will be a paper 1 question, because in a paper 2, you can simply use your graphic display calculator or scientific calculator, put the summation function in, put your values in, and calculate the sum, right? So that doesn't really give the question any value at that point. So method 2 is more of the formula based method, right? is when you have a complicated function, kind of the opposite, right? Complicated function, and when you have large number of terms, right? Say for 20, 30, even 20 can be a large number because every time we're gonna have to sit and calculate this function for a different value of I, it will get tedious. It will get really hairy and lengthy. So large number of terms. Okay. So um, suppose if we were to start with simple addition, right? In this case, I'll take a different color again. I'll take light blue. Okay, so if we took simple addition, what will our terms be, right? So our first term will be 7, 3 minus 1, which is 2, right? 7 squared. Then we would have 7 raised to the power 1, then 7 raised to the power 0, then 7 raised to the power minus 1, then 7 raised to the power, um, what do you say? You would have minus 2. This gives us 1, 2, 3, 4, 5, and you'd have 1, 7 raised to the power minus 3. Right, that is it. So this would be, and if you just take the sum of it, so if you do 7 squared plus 7 plus 1 plus 1 by 7 plus 1 by 7 squared plus 1 by 7 cubed, you will get your answer, right? And you can do that, you'll get your answer, put it in a calculator if you want, or leave it in some fractions if you want as well. If it's a paper one, I recommend leaving it in a fraction because I don't think you can find the decimal value of 1 by 7 cubed. Okay, now if you were, I'll just write this as method 1, right? So you're aware. Now if you do method 2, what I would do in method 2 is use the formula, right? Now, before using which formula to decide, I have to decide whether to use a convergent one or the divergent one. And the way I'll figure that out is by listing out like the first couple of terms. So I'll take the first 3 terms. Now I would write the first 3 terms here. I would still expand the function, but not fully like the way I did here. I would just take 7 squared, 7, and 1, right? So now if I get these 3 terms in the geometric sequence, what I'm going to do, first thing I'm going to do is find the common ratio, right? What I find that the common ratio is 1 by 7, right? That's pretty obvious. You can tell, every time the term is being divided by 7 or it's being multiplied by 1 by 7, right? Same difference. Okay. Now because the common ratio, right? The modulus of the common ratio is less than 1. So I can say, therefore, it is a convergent series. Okay, it will tend to infinity, and it will give me, when it tends to infinity, it will give me some constant value. However, the trick part is that they've given us the end part as 6. If this was infinity, then I would use the convergent series formula. But because we have to find the value of the first 6 terms, I'm going to use not the convergent, but the divergent. This is key here, okay? This is key to solving this question. Okay, so I'm going to be using the divergent, but if this was the infinity instead of the 6, then and only then would I be using the convergent formula. So I'm going to use a divergent formula here, which is u1 times 1 minus r raised to the power n upon 1 minus r raised to the power n. So I have my first term, which is 7 squared, which is 49. Okay, this is my first term. And I also have my n, which is 6, right? Because starts at 1, ends at 6, so there are 6 terms. If it was I is equal to 0 and goes to 6, then it'll be 7 terms. As simple as that, right? Nothing too fancy. So we have 7 squared as our first term, 1 by 7 as our common ratio, and n is equal to 6. All right, now sum of 6 terms. Let's put in the values of our formula. So first term would be 49, 7 squared. 1 minus 1 by 7 raised to the power 6. And, sorry, I wrote this formula incorrectly. It would just be like this. 1 minus 1 by 7. I'll just simplify it a bit. So 49 would be 1 minus 1 by 7 raised to the power 6. I took out the parentheses because you know what I was talking about. 6 by 7. What I'm going to do is I'm going to erase this part. I'm going to put the 7 on the numerator. So I'm going to write this as 7 cubed instead of 49, just to keep things as clean as possible. And I'm going to write it like this. Now at this point, you can simplify it a bit more if it's a paper 1 question and leave it as a fraction. But if it's a paper 2 question, and let's assume that it is for now, what you can do is you take your calculator and find the decimal value of the sum. So if you go ahead and do that, what we get is 7 cubed into 1 minus 1 by 7 raised to the power 6. So putting that into the calculator, we get 57.17, right? And I'm taking it to the 2 decimal places, so that's why I've done 57.17, right? That would be my sum, right? You can get a fraction value as well, but I've just kept it in decimal just because it looks much more cleaner. It's easier to visualize. All right, and again, this is a fairly type of a simple question. You can get this question, or you can get something a little bit more complicated. But the key here was to determine the 2 methods here, right? The 2 methods that I mentioned. Method 1, which is simple addition, or just the formula based. The second important part of this question was to know whether the modulus is greater than 1 or less than 1 of the common ratio, right? Now again, when it's less than 1, we go for the conversion. But here we were told that we have to find the first 6 terms, right? Not to infinity. Now again, one more thing you can take it as a hint is that if there was an infinity here, you can automatically tell yourself that the common ratio will be less than 1, right? If there's infinity, right? You can't get a sum to infinity for when the common ratio is greater than 1. Okay, when the modulus of the common ratio is greater than 1, you can't get a sum to infinity because the values will exponentially increase, right? You'll never get a constant value at infinity. You can only get that for when the common ratio is less than 1, right? That is another key thing to keep in mind as you move forward. All right, next question. A ball is dropped from a height of 600 meters. Each time it rebounds, it rises to 2/3 of the height it has fallen through. Find the total distance traveled by the ball before it comes to rest. Right? This is definitely an out-of-the-box question, and I highly recommend that you pause the video and give it a try. All right, let's get started. So before we start solving the question, let's get a very clear idea of what this question is telling us, right? So first, it says the ball is dropped from a height of 600 meters. Okay, 600 meters, right? So let's maybe say that this was the ball, and maybe this is the ground, right? And it's dropped 600 meters, right? So maybe we can say this height is 600 meters. Okay. So it says it bounces, and every time it rebounds off the ground, basically, it rises to 2/3 of its original height. So if I had to try to kind of visualize that, it would look like goes here and goes to 2/3, comes back down, and then 2/3 of this one. So it'd be something like this. Please, don't mind my drawing. It's not that great. So something like this, right? Every time 2/3 of the original height. So maybe 400 here, and then a height of 400 because it's 2/3 of 600, right? And then 2/3 of 400 would be 800 by 3, and then 800 by, and then 1600 by 9, right? Something like that. So that's what's happening here. Every time it's the height of the bounce is decreasing and decreasing, and slowly what's going to happen is even if you talk about real world application, it's going to go something like this, and then it's going to it'll continue bouncing, but the bounce will be so small that it'll make no difference to the distance that it's traveled, right? Now one more thing I like to mention is that although in the diagram I've shown the bounce to be something like a parabolic path, right? What it's actually happening, the bounce is actually going like this, hitting the ground and then going back up, right? That's actually what's happening, because Now, some of you might say, "Oh, it's going for following a parabolic path, so the actual height won't even be 600 meters; it'll be more than 600 meters." And I know someone's going to pick that out, and someone's going to say that. But I've just done this just so that everyone gets a clarity of what the question is asking us, right? What's actually happening to the ball is right here. It's dropped directly down, right? And then it bounces directly up, and it's basically bouncing in its original position again and again, so on and so forth, like this, right? So I just want to make that clear, so there is no confusion moving forward. Okay. So now, I've given you this idea. What the first thing that should come to your mind is that we're talking about sum to infinity here, right? And if you notice something, if you try to correlate this with your formulas, right? We have something called the common ratio and all those things, right? So what happens is that suppose we take h as 600, right? And every time it's being 2/3 of h first time, then again it's 2/3 and 2/3 of 2/3 of h, right? And then it's again 2/3, this time outright cubed h, and then 2/3 to the power 4h, and it's happening again and again, right? That is the height it's reaching every time it's going, right? So what's happening here is that you can see that the common ratio is being multiplied by 2/3 every time, and because 2/3, right, is less than 1, right, the modulus of the common ratio is less than 1, we have what is called a convergent series here, right? And it's also telling us find the total distance traveled by the ball, basically up and down, right? From the top to the bottom until it comes to rest, right before it comes to rest. So when will it come to rest? It'll come to rest after an infinitely long time, because technically, according to this thing, according to this pattern, the ball will continue bouncing. Even if the bounce is like 0.00001 meters, it's still bouncing, right? But it's so small, right? So what's happening is that we're going to infinity at this time. Time is tending to infinity. Time is tending to infinity. This means that it's going to go on forever. But what's happening at infinity, right, at this part? The height that it bounces is so tiny, it doesn't matter. Okay, even if we exclude all this information, or all this data values, or the value of the height here, this will hardly affect it. It's like adding 0.001 to 100, right? What's that going to make it? It's 100.0001. It's the same thing as 100. There's absolutely no difference. So this is the key information right here, to understand that we're talking about sum to infinity. And because it's a convergent series, and the common ratio here is 2/3. Okay, now let's clear up a few more things, right? Now, if we have to find the sum, what would we do? We would basically have, okay, so where would we start before that? Would we start it at here, or would we start it at here? Start here, where? Right, that is another key point. Like, where do we start finding the sum from? What do we make our first term we already know the common ratio is 2/3, right? We need to find our first term. How would we do that? Right? Now, we can start from here if we want, 600, right? We can start from here, and then it goes here, and then it goes here, right? We can make that it's very much possible. So let's make 600 our first term. U1 is 600, okay? U1 is 600. So if we make our U1, what's going to happen is that it's going to bounce, and it's going to go up, right? And then it's going to go down. It's going to go up this much. It's going to go down. It's going to go up this much, go down this much, right? So if we go and do that, what we can do is we can write, it goes this much distance, then it goes to this term, right? So what we can do is we can write sum to infinity, or we can just write, we'll write it as this. We'll make a small modification. What we'll do is we'll write sum is equal to 600 plus sum to infinity. Okay? And I'll tell you why. What I'm going to do is I'm going to exclude this part. Right? I'm going to write this as separately. Then I'm going to start my sum to infinity, which starts with 400, 800 by 3, 1600 by 9. Okay? Because as you can see, there's a pattern being followed right here every time. Right? Now, my sum to infinity here, let me put it like this, and I'll erase it, make it a different arrow. what my sum to infinity will be 600 upon 1 upon 2/3. Right? That's what it will be. So, however, there's one more thing to keep in mind, right? Some of you may have picked up on it by now. If you did not, that's perfectly fine. Like I said, it's an out-of-the-box question, so you might not get it at first. Now, what's actually happening here is that the ball is bouncing up, reaching to the height of 400, and then going back down, right? Right? It's going up here, then it's coming back down, right? It's going back up, coming back down. So what's actually happening is that it's going up 400, coming down 400. So it's actually traveling the distance of 400 meters twice, okay? That is what's happening here. So what I'm going to do here is I'm going to write this a 2 here, okay? That is the key part because it's going to go up once, come down, go up, come down, and we're going to assume that it comes down at the very end. So, it's going to end an even term. So it'll be all, the numbers are going to work out perfectly at the end. So this is another key portion to remember, right? This part, we're multiplying it by 2. Okay, so now we have cleared everything up and now we can just do the math. So what we have here is sum, or I'm going to write it, I'm going to write as capital D for distance. That's how I'm going to denote it as. So distance is 600 plus 2 times 600 upon 1 minus 2/3, right? So if we simplify that, what we get is 600 plus 1200 upon 1/3, right? I multiplied 2 with 600, I got 1200. I subtracted this, I got 1 by 3. So I get 600 by 2400. And what I get is 3,000 meters. Right, so the ball travels a total distance of 3,000 meters before coming to a stop. Now, again, technically, according to the question, the ball never comes to a stop, but the height the ball bounces after, a certain point of time, right? It is so small that it can be ignored, right? I mean, if we add 0.001 plus 3,000, right? What does that make? It makes no difference to the height, to the total distance. We can neglect it, right? And that was the whole concept and principle behind this question. All right, next question. George takes out a loan of $1,500 for his new apartment. He will be paying monthly installments. The loan has an interest of 12% per annum and must be repaid in 2 years. Calculate the amount that George has to pay each month if the first repayment is to be made 1 month after the money is borrowed and after interest is calculated. Also, calculate how much money George actually will pay for furnishing this apartment. Now, before I get started, I'd like to point out that this is a very typical IB question, which is found in Part B of Paper 2. I'm really confident that you will find this in multiple years if you take a look at them. And there's a very simple and straightforward method that if you just follow that every time, you will get full marks on this question, no questions asked. Okay, so before I start, I recommend that you pause the video, give it a shot on your own, and then follow the process that I explain. All right. I would also like to mention one more thing before I get started. In my previous video, I did a question using compound interest, and I had mentioned that the compound interest formula is not there in the IB booklet, and you might have to memorize it. That's wrong. It is there in the IB data booklet, and you can always refer to it. So even if you don't memorize it, it's not a big deal. I just wanted to point that out before I get started on this question. All right. So the first part of the information that's given to us that he takes a loan of 1,500. Okay, loan of $1,500. Right. So what we can say that 1,500 is the principal amount. So I'm going to label this as capital P and write 1,500. Okay. Second thing, it says the loan has an interest of 12% per annum. Okay, and must be repaid in 2 years. All right, that is the second important part. So I'm going to write it here. So 12% per year. Okay. That's what annum means per year. That's it. Annually, annum, same thing. Okay. That is another part. Okay. So now the key here is, first of all, we have to note that George. So let's solve this part first. I'm going to label this as part A and part B. Okay, we're going to solve part A first. Okay, part A. So it says George is going to be paying each month, right? All right. So he's going to be paying each month. So what we're going to do is we're actually going to divide this. All right. We're going to divide this by 12. Okay. So every month, if we divide 12% by 12, what we have is 1% interest every month, right? I mean, it can be any number, right? It could have been 24. It could have even been 20%. That would have had some decimal. But I suppose this question makes the numbers very easy to work with. So there we have it. So we're going to have 1% interest per month. Okay, that is the key information that we have, right? Now we're going to make a let statement. All right, in the let statement, what we're going to say is let x equal the amount of money paid by George, amount of money paid by George every month. Okay, because the question says every month he makes some repayment, right? To get rid of his debt, to reduce his debt that he has, right? So that is what X is, okay? Paid by George each month. Okay. That is what I'm gonna let X equal. All right. Okay. So now let's get an idea of exactly what the question is telling us. All right. So let's take this as orange. So what's happening here is that after every month, there's some interest being put on, and then George gets rid of some of the debt, right? So basically, what's happening is a 1% interest is being put on. So let's put a 1% interest on 1500. So note that the common ratio, or what it's being multiplied by, is not actually 0.01, right? It's not this. It's actually 1.01. Remember, like the question in our last video, we add the one because we're increasing the value. We have to increase it. So the only way we can increase it is by doing 1.01, right? That is the reason why we use 1.01. Okay, so what happens here is we have 1500 times 1.01. Okay, we have 1.01, and okay, you know what? I'll do this in blue, and then I'll change it again, and I'll use orange for some other time. So I'm gonna write here 15. Okay, not bad. So what I'm gonna write here is 1500 times 1.01 minus x, right? So this is the interest being put on after 1 month, and then this is the money that George pays to get rid of his debt, right? So I'm gonna label this, and I'm gonna put this in orange, and I'm gonna say, or I'm gonna actually no, I'm just gonna use blue for now, okay? So I'm gonna keep this in blue, and I'm gonna say after first month, okay? So after first month, okay? Now, second month arrives. So what's going to happen is that this much money is going to be remaining after the first month. So this entire value, right, 1500 times 1.01 minus x will be compounded, or will be multiplied by the interest rate again for the next month. And then another minus x will come in because after the next month has arrived, so George will pay off his debt again, right? So what's going to happen here is we're going to have, what I'm going to do here, I'm going to color code this very carefully, okay? So what I'm going to do is I'm going to take green, okay, and I'm going to do 1.01, okay, times this, everything in the blue right here, okay? So I'm going to go back to blue. I'm going to write 1500 times 1.01, okay? Inside, I'll have the minus x, okay? And I'm going to put the square brackets again in green right here. And then I'll do minus x. And this will be after second month. Okay. Now, Same thing, same process will be followed in third month, right? So in the third month, what's going to happen is another, again, this will be the money remaining, right? So we're going to have, again, 1.01. Now I'm going to put a curly bracket just to differentiate it. And then I'm going to go back to the green part, right? You understand what's happening, right? The pad, you see a pattern being followed here, right? So that is what I'm trying to indicate. This is the steps that you need to follow every time. What's going to happen is in the exam they're going to have some little different, right? Maybe they might have some dates that's different. Maybe the number of years are different, right? Maybe instead of every month it'll be yearly, something like that. These are the different variations that can arise. Okay, so let's continue. Right? So we would have 1500 in the inside for the first month. This is for the first one, right? And then we would have minus x, and then I would have to back it for the third month in red, which would be the curly bracket, and there we go, right? And this is after third month. Okay, this is right. Now, what can we do? Okay, so what I'm gonna do now is I'm gonna expand this. I'm gonna expand every single one of them. Okay, so what happens is and I'm gonna do this in orange. Okay, when I expand first part, right? I mean, all I can really expand, and what I'll get is nothing, too fancy. I'm just gonna get 1500 times 1.01 minus x, right? First one. Second one, what I'm gonna get here is 1500, right? Again, I'm gonna get 1500, obviously. 1500 times 1.01 squared minus 1.01 x minus x again, right? And then number three here, and number three here as well. What I'm going to have is 1500 times 1.01 to the raised to the power 3 minus 1.01 squared x minus 1.01 x minus x again. Okay, so what's happening here is, see, this was the first one. I multiplied this by 1.01 and then I subtracted x from it, right? I multiplied 1.01, so that's why I got squared here, and then 1.01 here, and then I subtracted by x. Again, I multiplied this by 1.01, so I got 1.01 cubed. I got 1.01 squared, and I got 1.01, and I subtracted x from it. That's the pattern that's following. So again, this is after first month, second month, and third month. So I hope you see the pattern that's being generated over here, right? So what's going to happen here is that our overall time is 2 years, or if I'm gonna convert that in months, it's 24 months. So what I can really say is happening here is that if let's use yellow now, right? So after 2 years, right? Or I'm just gonna put it in the parentheses as 24 months. Okay. So after 24 months, you can generate a similar pattern like this, right? So if I generate a pattern, what I'm going to have is 1500 times 1.01 to the raised to the power 24, right? Here, after 3 months, it was 3 raised to the power 3. So after 24 months, it'd be raised to the power 24, right? Nothing too complicated. I'm just following the same pattern every time, right? I mean, I could have done it every month and I could have expanded it, and it would have been really, really long, right? I would have, by the time I finished this question, my 2 hours of paper two would have been finished. And I don't even know, and the chance of making a mistake is so high here. So I'm going to use this general term, general process, and with this I'm going to work forward. Okay, so now the next term would be what? 1.01 raised to the power 23x. Then I would have minus 1.01 raised to the power 22x minus 1.01 raised to the power 21x, and then and I'm going to go all the way down to maybe 1.01 x minus x, right? This is where it ends, correct? Now, I'm gonna make a few adjustments here, right? Now I'm gonna have to make a few adjustments to get to my answer. Okay, so the few adjustments that I have to make here are that you see this pattern that's developing here, right? Ignore this part, but here, right? 1.01 raised to the power 23x, 1.01 raised to the power 22x, 1.01 raised to the power 21x, and all that, right? Now, one more thing I want to mention before moving forward is after 2 years, George is said to have, the condition says that George will have no money left in debt, right? He'll have paid his entire loan, including the interest, right? Including the interest. So after 2 years, this basically suggests, right, this expression every time we have, right, this expression or this expression, this expression, this expression, this expression, they all state the amount of money remaining, okay, remaining to pay to back, right, pay back, right? So after 2 years, right, George is said to have no debt left. That means he's paid all of his money back, right? So if he's paid all of his money back, the amount of debt left is zero, right? So what I'm going to do is I'm going to equate this to zero, right? And this becomes sort of my equation, right? Which I'm going to work with, right? Which I'm going to simplify, I'm going to condense, and I'm going to work with it. Okay, so after 2 years, George has zero money left to pay back to the bank. He has completed his entire debt, right? Nothing to pay back. He's all good, right? And this is why I equated to zero, right? This is the amount of money left after 2 years, which is zero. Fair enough. Okay, let's move forward. Now, like I was saying, I see this pattern being developed here, right? So what I'm going to do is I'm going to adjust some values here. I'm going to factorize some variables out here and there, and then we're going to have something, right? So if I work, if I do some manipulation here, what I'm going to get is 1.01 raised to the power 24 minus x. Okay, I'm going to factor out the minus sign and the x. So what I'm going to be left with here inside is 1.01 raised to the power 23 plus 1.01 raised to the power 22 plus 1.01 raised to the power 21 plus all the way up to 1.01 plus 1. Okay, I can put this as raised to the power 1, and it's 0 raised to the power 0, so I didn't bother putting it, but I hope you get it. All right, equals to 0. All right, now it seems exactly like a geometric sequence, right, or a geometric series, because the geometric sequences terms are being added, right? Exactly. Okay, so now all we have to do is we have to just add this up, right? So I'm gonna, maybe I'll highlight this in a better color, maybe. So maybe I can do something like this, and I'll say geometric series. Okay. So now all we have to do is we just have to use the geometric series formula, and when we're done, right? We just have to use the geometric series formula, and then we'll have a definite value here, and then we can just solve for x, and we'll have our answer, right? So if we let's continue with the yellow itself, right? Let's continue with yellow. So if we do that, what we're gonna have is, first let's compile some information, right? So Sn is equal to u1 times 1 minus r raised to the power n and 1 minus r. Look, I'm going to use the divergent formula here because common ratio is 1.01 and that's greater than 1, right? So I'm going to use this one formula, not the convergent, not the sum to infinity. Okay, cool. So now, what would my u1 be, right? Now, so I can take u1 to be either 1.01 raised to the power 23 or 1 itself, right? It doesn't matter. It actually does not matter, okay? It might seem like it matters, but it really does not matter, okay? Now, I'm going to take 1, right? Just to keep it numbers very simple. I'm going to make this my first term, and I'm going to make this my nth term, okay? And actually, that is the way it's supposed to be done, because if you think about it, if I take my common ratio, otherwise, if it's okay, so let me write the things down. Okay, so if I take right, okay, so if I take my first term to be 1.01 times 10 to the power 23, right? My n will be 24, right? Because this is 1.01 raised to the power 0. And this is raised to the power 23. So they're actually 24 terms, right? So my n will remain the same in both cases, right? And my common ratio would actually be my common ratio would be 1.01 raised to the power minus 1 here. So 1.01 raised to the power minus 1. That would be my common ratio. On the other hand, if I took u1 as 1, n would remain as 24, but my common ratio would be 1.01 only, right? It won't be to the raised to, you can say 1.01 raised to the power 1, but it's the same thing, right? So if I take u1 as 1, n will remain 24, like I said, but r will be 1.0, right? Now overall, right, this seems a lot more simpler to work with, right? You want to pick up the most simplest case. And in my eyes, this seems much more simple, right? More simple. So I'm gonna keep things as simple as possible, right? I don't want to make things unnecessarily complicated. So I'm gonna work with this. You can work with this. You can work out the math on your own. Put it in the formula. You'll get a big number for here. You get the same value actually. Doesn't matter. And then you can solve for x. You'll get the same value for x. You can knock yourself out. That's not a problem. I'm gonna go work with the more simple case because I like it that way. So now all I have to do is I just have to plug in for Sn. So let's go to the next page. So Sn, first term would be 1 minus, right? My common ratio is 1.01, okay? So 1.01 raised to the power n, right? Which is 24, all upon 1 minus 1.01. Now, obviously, you can tell, like, with this math, you'll need a calculator, and thus that's why I already told you before that it's a paper 2 question, right? So if I simplify this a bit more, what I get is S of n is equal to 1 minus 1.01 raised to the power 24 upon minus 0.1, right? And if I use my calculator, what I get, I'll get some value for it, right? Now let's just keep it at this for now, right? What I'm going to do is I'm going to substitute back into the original equation, okay? So if I substitute it back in, right? If I substitute it back in, what I'm going to do is I'm going to bring this part, I'm going to simplify this down into this, okay? So I'm going to get 1500. So I'm going to get 1500 into 1.01 raised to the power 24 minus x, right? Minus x. And I'm going to make a few adjustments here. I'm going to write this. I'm going to swap the places around. I'm going to multiply the numerator and denominator by minus 1. So I'm going to get 1.01 raised to the power 24 minus 1 upon 0.1. Okay? That's what I'm going to do. So now I've done that. So what I can do is I've done this. I've done that. Now I'm just going to put this part in. So I'm going to get 1.01 raised to the power 24 minus 1 upon 0.1. Okay, this is done now, and I'll equate it to 0, right? And I'll equate it to 0. Okay, again, 1500 1.01 raised to the power 24 is equal to x. Okay, x into 1.01 raised to the power 24 minus 1, 0.1. Okay, and then if I simplify it a bit more, I mean, which I really don't need to, but I'll just do it for the sake of simplifying. What I can do is x equals 15 times 1.01 times 24 all upon. I just want to point something out. I made a small error here. I should put 0.01, 0.01, 0.01, 0.01 here. Okay, so now I get 1.01 raised to the power 24 minus 1. Okay, that's it. So if I simplify this, what I get is approximately 70.61, right? Now, x, right? And what did I tell x to be? I said, let x be the amount of money paid by George each month, right? Paid by George each month, right? So calculate the amount of money George has to pay each month, right? That's the same thing, exactly the same thing. So I just answered part A, right? So all I have to do is write x. I can just, I'll just put it up here so it's easy for me to calculate, right? 70.61. So dollars 70.61. He pays. That means what this answer means is that to get rid of his debt in exactly 24 months, George pays $70.61 every time at the bank, every month at the bank, right? So at the end of 22 years, he'll have no debt left. Okay, that's it. That's what this part A means. Okay, now let's get to the next part, part B. Also, calculate how much money George actually will pay for furnishing this apartment, right? So it's actually much simpler than it looks. Okay, so let's mention part B here in a different color. Okay, I'll take pink. Okay, so part B. Now, George pays, right, dollars 70.61 per month. Okay. Now, note that they're asking how much money George will actually pay for furnishing the apartment. Now, George is paying this much money every month, and he's paying for 24 months. Pays for 24 months. So doesn't it make sense that 24 times 70.61 is the amount of money George will actually end up paying, right? Think about it, right? He's depositing $70.61 in the bank every month to get rid of his debt, and he's doing that for 24 months. So 24 times 70.61 is the actual money he pays, right? So the amount of money that he actually pays is $16.95, right? Approximately again. Right? That is the money. That is the amount of money he pays. So basically, he borrows 1,500, borrows 1,500, and actually pays 16.95 to the bank, right? Because of the loan and the interest charges, right? That's it, right? That is the answer to this question. So I'll just write it up here: 16.95. 16.95. Okay, that's it. All right, so this was the last question for today, and yeah, that's about it. So in the next video, we'll take a look at properties of geometric sequences and series. I'll discuss a few important properties and direct questions that can come from them. So very similar to what I did for properties with arithmetic sequences and series. So that's all for this video, and I'll see you in the next one. Bye bye.